in this class we discuss about molecular velocities. As in our earlier lectures we discussed about the kinetic gas equation, kinetic energy P v equal to 1 by 3 m n c square. In the kinetic gas equation, P v equal to 1 by 3 m n c square. C is the molecular velocity, where that means velocity of gas molecules, and here specifically it is RMS velocity, right. What is RMS velocity? RMS velocity means root mean square velocity. RMS velocity means root mean square velocity. What is root mean square velocity? First of all, what is how do we determine this molecular velocity and all is what we discuss now. As in the postulates of kinetic theory, we told the different gas molecules will have different molecular velocities. Some gas molecules may have very low velocity, some gas molecules may have very high velocity, some gas molecules will have moderate velocity. This is what already we told. So, based on this, so when a distribution plot has been drawn for the fraction of molecules possessing a particular velocity, the graph is like when a graph is drawn for fraction of molecule f versus velocity, fraction of molecule versus velocity when a graph is drawn. Fraction of molecules means the fraction of molecules possessing certain particular velocity, right. Then what it is observed is that the fraction of molecules possessing very low velocity or very less, with increase in velocity the fraction of molecules possessing that particular velocity increases, and after that after reaching certain maximum again they will decrease. This is what it is found, right. So, the meaning of this is that now this ranges from very low to very high. So, from this what you can understand is that the observations that we can make from this graph is that molecules with very low velocity and very high velocity means this fraction very low and this is very high velocity or very less. And with increase in velocity, fraction, that is f, which is equal to dn naught by dn by dn naught or n by n naught, otherwise I will put it n by n naught, means n is the number of molecules with a particular velocity, n naught is the total number of molecules. N is the number of molecules with a particular velocity and n naught is the total number of molecules in the given amount of gas. Suppose if you have 1 mole of a gas, then n naught will be Avogadro number. In that Avogadro number of molecules, how many are having a particular velocity? That is what we are drawing. So, with increase in velocity, fraction of molecules also increases first, increases initially, reaches maximum and then decreases. Increases initially, reaches maximum, This is the maximum velocity that can be possessed by any particular molecule. This is the velocity possessed by maximum number of molecules. Again I repeat, this is the velocity possessed by maximum fraction. Right, and after reaching maximum again it decreases, means the higher velocity from here to here, this is low velocity, this is moderate velocity and this is high velocity, like that if you categorize, then the molecules possessing very low velocity, very high velocity are very less, moderate velocities are maximum, right. So that is what he says. And also another thing is that if you draw another graph at another particular temperature, this is of course a particular temperature T1 Kelvin, and at another temperature if you draw, what also it is observed is, this is a kind of graph that what we get. This is at a temperature T2 Kelvin. Now T1 Kelvin and T2 Kelvin, the graphs that are drawn at two different temperatures T1 Kelvin and T2 Kelvin if you observe, then one more inference that what we can draw is that with increase in temperature, velocity of all gas molecules is increasing. Velocity of all gas molecules is increasing. No doubt that for maximum fraction here you are having increase in velocity, but at the same time, fraction of molecules with an increased velocity are decreasing. Meaning is, if you compare the two curves, here the velocity of molecules relatively less for a particular fraction. If you take here for a particular fraction, if you take the 2 points, this is the velocity at T1, this is the velocity at T2. So this is, if you note it them as V1 and V2, for same fraction at T2 Kelvin the velocity will be high. So basically point is, with increase in temperature molecular velocity increases. That is obviously quite known, all of us can easily understand that with increase in temperature kinetic energy increases. So obviously, as of course the mass being same, it is nothing but the molecular velocity is increasing. But if you look at the height of the peak, so here what is happening, the peak is shifting towards the right hand side, that is increased velocity. Peak is shifting towards the right, that means the peak is shifting towards the right, means the velocity of a particular fraction of molecules is increasing. But at the same time also what you can observe is the height of the peak is decreased. Height of the peak is decreased means the fraction of molecules possessing that particular velocity is decreasing. So the curve is getting flattened over here. Here you will have a sharp peak, but here you will not have a sharp peak, but rather the curve is getting flattened, means the height is getting decreased. That means the fraction possessing that particular velocity is decreasing. This is what the inferences that you can draw. Now from these things, what the difficulty is that as the velocities of molecules are having a very wide distribution, right. So if you are giving one particular velocity, for example 100 meters per, the velocity of gas molecules, suppose if the velocity of gas molecules are ranging from 10 meters per second to 400 meters per second, suppose if the range is 10 meters per second to 400 meters per second, then there is certain fraction which is having a very low velocity 10 meters, which is having a very high velocity 400 meters. So then if we have to express the molecular velocity in one single term, it is very difficult to give, because even if you take first it was proposed to take the average of all. If you take the average of all, say suppose if you are getting the average of all as something around 100 or 150 or 200, If you say the average velocity is 200, that means, but it gives an impression that most of the molecules are moving with the almost all the molecules are moving with the velocity of 200 meters per second, which is not true, because your range is so wide. Suppose all the molecules are ranging between say 190 to 210 meters per second. For this, if you take the average as 200 meters per second, we can understand. But for this whole range, taking any either 200 or 250 or 100 is not an acceptable value according to statistics. The statistics will not accept of giving any one particular velocity to all the gas molecules. So, first it is given the average velocity, but when it is given the average velocity, the problem is that, as we told, that average of all that, either it may be 200 or 100. At the same time also there is another possibility that if two particles are moving in opposite directions, but with equal velocity, if it is 100 meters per second and this is minus 100 meters per second, then average when you take, there is every possibility that the average even may become 0 also. The average velocity also may become 0, because this is moving in positive, this is moving in the negative directions. So, average is becoming 0. Average is becoming 0, and if you say that the molecular velocity is 0, it gives an impression that the gas molecules are not in motion. The gas molecules are at rest. 0 meters per second means the molecules are supposed to be at rest, but it is very clear that no gas molecule can be at rest at any time under any conditions. So, the term average velocity is found to be not suitable. Then another proposal that is made is this velocity possessed by maximum fraction, that is what we call most probable velocity. This is what we call most probable velocity Cp. This is C bar, this is CRMS. Cp is the most probable velocity, that is the velocity possessed by maximum fraction of molecules. Then C bar is the average velocity, is what I told you now, that it is the sum of the velocities of all the gas molecules divided by total number of molecules, that is C bar. But C bar, as I told, can become 0 also. Cp if you take, no doubt it represents most of the molecules, but definitely it cannot represent the fraction of molecules having very low and very high velocities, right. So, another term that is given is, another velocity term that is suggested is CRMS, which is considered to be more appropriate while deriving the kinetic parameters of the gas molecules. What is this RMS velocity? RMS stands for root of mean of square of velocity, root of mean of square of velocities, RMS velocity. So, the Cp, C bar, CRMS, these are the different types of velocities that have been proposed to consider while dealing with kinetic parameters of the gas molecules. Now, how to determine the Cp, C bar, CRMS? That is what next we are going to look at it. So, again when we look at the graph, so this is the velocity possessed by, this is the maximum fraction. So, the velocity correspond to that is Cp. Cp is most probable velocity. Then the next is C bar. C bar is average velocity. Next is CRMS. RMS velocity. This is a temperature T1 Kelvin, this is a temperature T2 Kelvin, is already we told, and T2 is greater than T1 with increase in temperature. With increase in temperature, velocity of all the gas molecules is increasing, but the fraction possessing a particular high velocity is getting decreased. And for this T2 again, if you take the similar graphs, then this will be Cp dash, C bar dash, CRMS dash, something like this. Okay, this is CRMS. Now, what is Cp, C bar, CRMS mathematically? This is graphically, right? Mathematically, equation wise, if you take C1, C2, C3, etc., or velocities of each gas molecule, velocity of each gas molecule, then Cp is the velocity possessed by maximum fraction, velocity possessed by maximum fraction, and it will be given as that. From this, if you look at it, Cp, C bar and CRMS, if you look at it, Cp less than C bar less than CRMS. So, Cp is equal to under root 2 RT by m or under root 2 PV by m, and C bar is actually nothing but average C1 plus C2 plus C3 plus Cn by n, which is under root 8 RT by pi m or under root 8 PV by pi m, or even you can take under root 8 this is 8 RT by pi m, and this V by m is nothing but m by V is density. So, V by m is 1 by d. So, 8 P by pi d, and this also you can write under root 2 P by pi d. This is in terms of temperature, this is PV, this is d. When density is given, pressure volume are given, temperature is given. These are the different formulae that we take. And CRMS is, as I told, because C bar, there is a possibility that when you are considering the sign of the velocity, the average likely to be 0 or even very less. So, in order to avoid that, root of mean of square of velocities is what it is taken. So, root of mean of squares means C1 square plus C2 square plus C3 square, etc., right. These are the squares, mean of this, that is divided by n, root over this, right. This is RMS velocity. So, that here one can avoid that sign of problem, that it will not be 0. C1 square plus, as you squared it up, you can avoid the negative sign. So, and this is equal to under root 3 PV by m, 3 RT by m. So, this RMS velocity is given with the formula 3 PV by m or 3 RT by m or 3 P by d. Okay. So, from all this, if you look at it, Cp here itself you can understand that for any given quantity of gas molecules at a given temperature, Cp less than C bar less than CRMS. That is, they are in the ratio of, again from this if you look at it, Cp is to C bar is to C RMS is equal to root 2 is to root 8 by pi is to root 3. This is also what we can give as 1 point, this is 1.1 is to 1.12 is to 1.22. This 1 is to 1.12 is to 1.22. This is the ratio of the different molecular velocities. So, these molecular velocities are given by statistical distribution. By taking the statistical distribution of different velocities, I mean the velocities of all the different molecules, then Cp, C bar, Crms are given, and in which Crms is found to be most appropriate while dealing with the kinetic parameters of the gases. So, that is the reason, that is actually the one that have been taken here. The C, this C is RMS velocity, but of course the ratio is the difference is very less, 1 is to 1.12 is to 1.22. Now, from this again the Graham's law wise, if you look at it, this PV is equal to 1 by 3 MnC square. Diffusion is nothing, rate of diffusion is nothing but velocity with which the gas molecule is moving. So, from this you can see that at a constant temperature, PV being constant, C square will be proportional to, C square will be inversely proportional to molecular weight. So, ratio of diffusion R1 by R2 is nothing but C1 by C2 is equal to root over M2 by M1. So, that is what even the diffusion wise you can say you can explain this, I mean the ratio of velocities, how they are related to the molecular weight already in the diffusion itself we have seen. So, this is about the molecular velocities. Now, what are all the different other kinetic parameters? So far, in the beginning of the theory itself we told that this is the theory based on the kinetic parameters of the gases. Kinetic parameters means the velocity, kinetic energy and other things. So, in this we have seen already the molecular velocities, the kinetic energy. Now, what are the other kinetic parameters? We have to look into it. This is what we have to discuss now. Now, this how we got the molecular velocities, that Cp as under root 2 RT by M, C bar under root 8 RT by pi M, C RMS under root 3 RT by M, all this. But this is all actually Maxwell's distribution. According to the statistical distribution given by Maxwell, here different scientists, Maxwell, Boltzmann, these are the scientists that have studied the statistical distribution. So, also in fact we call them as Maxwell-Boltzmann distribution curves. This curves what we have drawn are also said to be Maxwell-Boltzmann distribution curves. Now, mathematically what it is given is, suppose if you consider if you take a fraction of molecules possessing that one particular velocity nu by n naught, that if you take according to Maxwell and Boltzmann, this dn u, the u here is velocity, by n is equal to 4 pi into m by 2 pi r t power 3 by 2 into e power minus mu square by r t into u square du. This is a mathematical equation that is given by Maxwell-Boltzmann. With change in velocity u, or for fraction of molecules possessing that particular velocity to the total number of molecules, this is the distribution. From this what we can understand is that dnu by n, that is the fraction of molecules possessing a particular velocity, is directly proportional to T. With increase in temperature, that increase, and as we know very well that velocity and kinetic energy and velocity u or c, whatever it is proportional to root T, square root of temperature. And also dnu by n is then proportional to 1 by m, and this is in turn proportional to u square, right. Fraction of molecules possessing a particular velocity is inversely proportional to molecular weight and directly proportional to u square, that is square of velocity, right, and u in turn is proportional to square root of T. So when u is in turn is proportional to T, finally what we can write is, therefore in totality dnu by n is proportional to T by m, because u square, the dnu by n is proportional to u square, but u is proportional to root T. So when u is proportional to T, dnu by n is proportional to what? T. This is because when u is proportional to root T, u square is proportional to T. So dnu by m is proportional to T and inversely proportional to m. So therefore dnu by n is proportional to T by m. So from this actually it is given that ump are nothing but Cp, what you are writing. This is a standard notation, but this is the notation what we are using, Cpe. This Cp is proportional to, then Cp is equal to under root 2RT by m. At constant temperature, this is nothing but equal to 2PV by m, and this is equal to 2P by d. This is what already we have written. So this is actually the statistical distribution equation from which at a particular, for a given velocity or fraction of molecules possessing a particular velocity in the overall distribution, how we can determine is by this. This is a graphical representation, this is a mathematical equation. From this all the relations have been derived, and finally the equation for Cp, C bar and Crms as given as, from this already we know that Cp C bar Cp is to C bar is to Crms is equal to 1 is to 1.12 is to 1.22. This is what already we have written. So this is how the total, based on the statistical distribution, all molecular velocities graphically, mathematically they have been derived, they are shown, and this is what the most appropriate velocities that what we should use, right. Now after this the other kinetic parameters like collision diameter, collision frequency, mean free path, also we have to look at it. So about the kinetic parameters of the gases, so far what we have seen is the kinetic energy. Kinetic energy is equal to 3 by 2 kT or 3 by 2 PV. This is per molecule, and overall this is the one, and velocity Cp, C bar, Crms. These are the ones that already we have discussed. Now collision diameter. What is collision diameter? Collision diameter is nothing but when molecules are coming for a to nearest approach, when two molecules are coming to their nearest approach, so that their repulsions are overcome, attractions and repulsions will compensate each other. The optimum distance, this is nothing but optimum distance between centers of two colliding spheres at their closest approach. At their closest approach. When the molecules are coming from infinite distance, when they are coming closer for a collision, they will come very close for collision, but due to repulsion again they will go little apart and they will maintain an optimum distance, so where the attractions and repulsions are compensated each other. That optimum distance that they will maintain, in that situation the distance between the centers of the two such colliding atoms is what we call collision diameter or molecular diameter, right. So, this collision diameter is represented with the symbol sigma. Here this distance is what we call a collision diameter. Collision diameter will always be slightly more than the sum of the radii of the two colliding spheres, because there will be some optimum gap between the two colliding molecules, right. And so, this collision diameter is sigma. Then second thing is the collision frequency. Collision frequency. This collision frequency is nothing but number of collisions in unit time. Number of collisions in unit time for molecules moving with certain velocity c. Again here c by default meaning is it is c RMS. So, for that this collision frequency is equal to root 2 pi sigma square root 2 pi sigma square n star u RMS, means collision frequency, number of collisions that are taking place in unit time. Number of collisions taking place in unit time is what we call it as the collision frequency, right. That is equal to root 2 pi sigma square, that is collision diameter, right. So, it will give you actually the area in which the collisions that are being taking place and the fraction of molecules having that particular velocity, and URMS is that velocity. So, it is n star is the number of molecules that are possessing a particular velocity u in a volume of space of about 4 by 3 pi r cube if you take a spherical volume. But of course, this is 2 under root 2 square root 2 pi sigma square n star URMS is the collision frequency, number of collisions that are taking place in unit time per unit volume of the molecules, all the molecules, that is n star, all the molecules having particular velocity URMS. This is the collision frequency. Then most important of all this is mean free path lambda. Mean free path lambda. What is this mean free path lambda? Because here as you have more molecules, suppose in the vessel you have large many number of molecules, then one particular molecule will travel different path, right, like this it will travel. Then mean free, what is mean free path? As it is undergoing many number of collisions, mean free path is nothing but, suppose if you take these two particles, then the distance moved by this particle towards this particle to have a collision is this, but this distance not necessary to be same as this distance, this is again not necessary to be same as this distance. So, each molecule will move to different distances before it is undergoing a collision or in order to undergo a collision. Now, what is this mean free path? Mean free path is obviously nothing but average distance that a molecule moves, a molecule travels in order for a collision to take place. The other way around, we can define this mean free path also as that it is the average distance average distance travelled by the molecule, average distance travelled by molecule between two successive collisions. Suppose if you consider only two molecular system or if you have one molecular system, suppose here you have a particular molecule, this particular molecule will hit the wall of the vessel. Now again for this molecule to hit the same wall, then the distance that it travels must be 2L centimeter. If this is L centimeter, then the distance travelled by one particular molecule to have collision on the same wall, same surface of the vessel. In the kinetic gas equation we consider this particular case. Okay. Suppose if the molecule initially expected that it has a collision on this wall, from that collision it goes back, comes again towards the same wall to have one more collision on the same wall. So that particular molecule is travelling a distance of 12 centimeters in order to have a collision on the same wall. So the meaning is that the path travelled by that particular molecule between two successive collisions on the same wall, it is 12 centimeter. Like that, among the now intermolecular, this is of course with the wall I told, between the molecules, intermolecular collisions when they are taking place, the average distance travelled by molecule between two successive collisions is what we call mean free path. And this mean free path lambda will be given as eta root 3 by PD, where the eta is viscosity of the gas. Obviously, how thick the gas is, what is the intermolecular force, it obviously matters the path travelled, and of course P is the pressure and D is the density. Now this lambda is equal to eta root of 3 by PD, and this lambda in fact is equal to velocity by collision frequency. This collision frequency, if I represent it with the symbol F, because this is velocity by frequency, velocity distance travelled in unit time, distance travelled in unit time by number of collisions in unit time, that is nothing but will give you lambda. So when this gives you lambda which is equal to u by f, and this is now equal to u again the velocity by root 2 pi sigma square n star u. Now u cancels. So from this what I can say is this lambda is equal to 1 by root 2 pi sigma square n. Lambda is equal to 1 by root 2 pi sigma square n. So the other way what you can say is that collision frequency and mean free path are in inverse relation, right? Only the difference is here you have to multiply with the URMS. So if you consider that this being a constant, then what you can say is lambda is inversely proportional to the collision frequency. Mean free path is inversely proportional to collision frequency. Now this mean free path, what are the parameters on which this mean free path is dependent? The mean free path is of course, as you can see it over here, is dependent on viscosity of the gas, that is the thickness, the density, everything. So from this you can see that lambda is inversely proportional to P, lambda is inversely proportional to D. So from this lambda is proportional to 1 by root P, lambda is proportional to 1 by root D, and lambda is proportional to T, because URMS here this is lambda is equal to this URMS is proportional to T as a velocity. Now mean free path obviously will proportional to temperature. With increase in temperature, path travelled also will increase, right? And at same temperature, at same volume, at some volume if P and T are changed. If P and T are changed at same volume, there will be no change in the mean free path, because one compensates the other. When you are writing it as 1 by root P, or when you are taking lambda is proportional to 1 by P or is proportional to T, then at constant V, then you one compensate the other. Lambda at constant V, if P and T are changed, lambda will not change, because at constant volume, if pressure and temperature both are changed, one compensates the other. As a result, there will be no change in the mean free path. So, this collision diameter is of course the sigma, the closest the distance at the closest approach of the two colliding molecules. Collision frequency is the number of collisions that are being taken place by molecules moving with a particular velocity URMS with collision diameter sigma as root 2 pi sigma square n star URMS. Mean free path is inversely related to collision frequency. So, mean free path is equal to 1 by root 2 pi sigma square n star, right, and from this you can write lambda is proportional to 1 by P, that is inverse relation, lambda is proportional to density, and lambda is inversely proportional to density, and lambda is directly proportional to temperature. So, the factors that affect the mean free path are, because in the previous 1 or 2 examinations regarding the mean free path theoretical questions have been asked. So, one has to be very clear as far as this mean free path is concerned, what are the factors that will affect the mean free path. The factors that will affect the mean free path are pressure, density, viscosity, temperature. These are all the various parameters that will affect the mean free path. Now, for example, pressure where it varies, that if you take into consideration, how the mean free path varies, if you look at it, if you take air molecules of the air at sea level and at some higher altitude, if you take at sea level, at mean sea level, MSL, mean sea level, for air, this lambda is equal to 6 into 10 power minus 6 centimeters, but at 100 kilometer altitude, this lambda is equal to 10 centimeters, that is means increase by 1,000,000 times. What is the reason? Because at a higher altitudes, what will happen to the pressure? Will be very, very less. So, the mean free path, as lambda is inversely proportional to pressure, lambda is increased enormously. From a normal mean sea level to 100 kilometer altitude, when you compare, it is coming out to be, the mean free path is coming out to be 1,000,000 times more. So, that is what from that easily you can understand. So, these are the relations. Now, this is so far what all we have discussed as the gas laws, ideal gas equation, theoretical explanation for the ideal gas equation and behavior of ideal gases, that is kinetic molecular theory of gases, the postulates of kinetic molecular theory of gases, kinetic energy of gas molecules, velocities of gas molecules, kinetic parameters like frequency, collision frequency, mean free path and all we have discussed. So far what we have discussed is all about more or less, even including the diffusion and all, the characteristics, behavior of theory and practical observations related to the behavior of ideal gases. Now, we have to go for deviation of gases from ideal behavior, the second part of the gaseous state. So far what we did is the first part of the gaseous state, second part now we have to look into it. In the second part, it is all more theoretical, in the first part it is more a numerical type. Now, we have to go for deviation of gases from ideal behavior, compressibility factor, then of course, van der Waals equation and all we will see in the next lecture.